This will introduce some of the newest modelling features that will particularly be useful for building engineers. The example used in this video is a 12-storey reinforced concrete building. The first level height is 4 metres while the rest is 3.2 metres. Let's start with a typical floor layout. Here is a typical floor layout, consisting of a number of beams, columns, walls, and a lift core. We will start the modelling process by extruding nodes to make columns. And extruding members to make 300mm walls and the lift core. The beam section and material properties have been predefined. But if you want to review them, simply click one of them and choose View/Edit Member Properties, and then click on the Shape Builder. In this model, the beam section was chosen as 500mm by 300mm. Let's assume the column sections and material. We will be using the same 32 megapascal concrete for all elements in this example. The column section is 600mm by 600mm. To mesh the walls, I am just going to simply subdivide each big wall panel into smaller elements with the element size of 0.5 metres. Note that you can change the transparency of each type of element. Next we will mesh the slab. To mesh the slab, the easiest way is by selecting all the members that make up the boundary of the slab, and the members that define the connection line between the floor slab and the walls. Then right-click, choose Mesh Tools, and choose Generate Plate Mesh from Members. At this point, we have basically done the modelling of a typical floor. We will just need to copy it up to make up the similar floors using the Copy Floors tool. Source elevation is simply the elevation of the floor you want to copy from. You can manually enter the value or select elevation and then click on anywhere on the source floor. Target floor elevations are the elevations where you want the new floors to be at. You can tabulate the target floor elevations here or generate it from elevation guidelines that you initially set up. Now that you've done the modelling part, in the next part of the video, we will show you how to assign the seismic loads on the building, including the accidental torsion eccentricity required by the AS1170 code. Let's define some of the typical load cases for the building. Load case 1. Load case 1 is the self-weight of the structure. Load case 2 is the additional imposed dead load. Load case 3 is the total dead load, which is a combination of load case 1 and load case 2. Load case 4 is the typical live load for an office building, 3 kilopascals. We are particularly interested in load case, which is a combination of dead load plus 0.3 live load. We will be using this load case as a mass source load case for dynamic analysis later. To create this mass source load case, we will use a tool to convert static load case to mass case. We are now converting static load cases 2 and 4 to mass cases 10 and 11. And then we will combine load case 1, which is a self-weight, and load case 10, which is the additional dead load, and 0.3 load case 11, which is live load, as load case 12. This will be the mass source load case, which later we will use for dynamic analysis. Again, this is not a complete set of load cases that you must consider. These are just a few of the load cases of interest for the demonstration purposes. At this point, we can quickly run a static analysis to see if there's any problem with our model. Let's analyse the dead load case only, LC3. Once the analysis has completed, we can turn on the deflection contour. We can isolate a single floor to examine the deflection. It looks like the deflection seems excessive in an area of each floor. This might be a problem because the deflection might be even larger once we have taken crack sections and the live loads into account. To account for cracked sections of beams and columns, the section factors can be used to reduce the flexural rigidity of the columns and beams as required by codes. Different codes will require different factors. Usually for beams and slabs, use a factor of 0.4 and column 0.7. Similarly, you can reduce the bending stiffness of the plates by using a smaller bending thickness. But note that the bending stiffness is not linearly proportional to bending thickness, but to bending thickness to the power of 3. An example is that if you reduce the bending thickness by half, the bending stiffness will reduce by 8 times. If you want to reduce the bending stiffness to 40% of the original plate with actual thickness of 210 mm, the value for bending stiffness you should enter is 155 mm. Let's create a typical serviceability load case G plus 0.7 Q. Load case 6. And run the analysis with the reduced bending stiffness of the beams, columns, and slabs. The deflection under a typical serviceability load case seems okay, especially as this deflection is resulted from a span whose length is roughly 9 meters. 1 or 2 columns in this area might be ideal to reduce the overall deflection. However, it is not the focus of our example. Next, we will show you how to assign diaphragm and seismic loads. To assign diaphragm for floors, click on Loads, then Generate Diaphragm Loads. There are 2 main parts in this form. The first part consists of diaphragm options, including types of diaphragms, eccentricity, and floor elevations. There are 2 types of diaphragm currently supported by space gas, including rigid diaphragm and semi-rigid diaphragm. If you choose the option Rigid Diaphragm, the process assumes that the diaphragm is rigid enough so that no axial, bending, and shear deformations are expected in the plane of the diaphragm. Thus, the diaphragm is displaced as one rigid component under applied lateral loads. Storey shears are distributed to supporting lateral members based on their relative rigidities. Thus, stiffer members attract more storey shears. Diaphragm mass is lumped at diaphragm's mass centre, and it has 3 components: mass in 2 horizontal directions and a round vertical axis. In other words, rotational inertia of diaphragm mass. If you choose the option semi-rigid diaphragm, the distribution of horizontally applied loads through diaphragms to lateral load resisting elements depends on relative rigidity of diaphragms and the resisting lateral elements. Eccentric loading. Several building codes require eccentric loading on diaphragms to account for accidental torsion effects. Referring to models with rigid diaphragms, such eccentric loading is accomplished by simply shifting loads to a new position that accounts for eccentric distances. For instance, concentrated storey loads for seismic load cases are first calculated at diaphragm's mass centre and then they are applied at their shifted locations. For wind load cases, a similar process is followed. Storey wind loads are calculated based on building profiles, one for X and one for Y direction, and then they are lumped and applied at their shifted locations. On the other hand, for models with semi-rigid diaphragms, the above procedure is not applicable since such diaphragms are meshed and loads on these diaphragms are not concentrated at certain location, but they are distributed over the diaphragm for seismic or dynamic load cases, and they are applied along the building edges for wind load cases. To address these issues for semi-rigid diaphragms, different methods are implemented. First, space gas determines the centre of mass of each floor. Based on the direction of the seismic load or wind load, the program defines a line that goes through the centre of mass. Then the nodal masses of the left and right hand side of this line are adjusted so that the total mass stays the same, but effectively the centre of mass shifts to a new location that accounts for required eccentric distance. The eccentricity percentage input here is the percentage of the width of the building perpendicular to the direction of the load at each diaphragm. The second part of the form is the seismic options. You can specify the start load case for seismic loads. Usually the vertical mass does not significantly affect the seismic analysis, so we can leave it out in this example. Lateral mass should be included, obviously. And the third option is whether to lump mass at floor levels. What this means is that all the masses between the floors, such as from the lift core, or walls or columns, are lumped to the nearest floor and assumed to be part of that floor during the dynamic analysis. The third part of the form is for wind load options. Space gas automatically detects the height of the building and calculates the wind load profile along the building height based on the given code and user provided information. In this example, we are using wind code AS1170. Assuming the building is in Melbourne, region A1. We will just use the default input parameters such as MS, MT, etc. You can then click on View Wind Calculations to see all the calculated results related to wind load. Or click on Chart Wind Loads to see the wind load profile along the building height. Make sure that you have entered the correct mass source load case and hit Generate Forces. This form is a quick summary for diaphragm load results, showing centre of mass for each floor, the cumulative centre of mass, and each mass component. It also shows the magnitude of wind load acting on each diaphragm. In the next section, we will perform the dynamic frequency analysis. This includes 5 load cases corresponding to cases where the masses are lumped to the centre of mass, and 4 eccentric locations respectively. Once the analysis is complete, a mass participation factor is shown. If the mass participation factor is less than 95% in a direction of interest, you should increase the number of modes and reanalyze the dynamic analysis. You can turn on the dynamic modes to examine the results. Next, we will run a spectral response analysis. A spectral response analysis calculates the effect of an earthquake on a structure. The properties of the earthquake are defined in code-specific spectral curves. response spectra that are supplied with space gas. Each spectral curve is a graph of acceleration in terms of g's versus period in terms of seconds, and is derived from the time history record of a ground vibration for a specific level of dampening. They are not dependent in any way on the properties of the structure being analysed. A built-in graphical spectral curve editor allows you to modify or create your own response spectra and save them to a spectral curve library. You can define spectral load cases, each of which references a list of modes, a spectral curve, and mass load case and a direction vector. It is common practice to have a spectral load case for each of the two horizontal orthogonal building directions, plus various combinations of them, with the use of combination load cases. Most earthquake loading codes require you to consider extra earthquake directions between two basic perpendicular directions. This usually involves combining the actions in one direction with 30% of the action in the perpendicular direction. We can easily add these as extra combination load cases. For an accurate spectral analysis, it is important that the spectral load cases have been defined correctly and that appropriate combinations of the spectral load cases have been specified. If horizontal base shear scaling is activated, the results will be scaled up if the total reaction in the vector direction is less than the user-defined proportion of the total static force or a user-defined percentage of the total mass. Once you have analysed the response spectral load cases, you can now proceed to use deflections, forces, moments, and reactions in exactly the same way as it had come from static analysis. Combinations can be further combined with other load cases such as dead load and live load to create new combination cases for analysis. Again, this is a brief introduction to seismic analysis of structure using space gas. For more details, please refer to the Space Gas Help Manual. Another important aspect with modelling and analysing reinforced concrete high-rise buildings is the consideration of storey shear and storey drift. Space Gas provides tools to make such analysis easier and user-friendly. Let's consider load cases from 201 to 212. These are wind load cases that have been automatically created previously when we set up the diaphragms. You can access the storey shear by right-clicking anywhere on the main window. Then, define the elevations that you would like to see the shear forces acting on. The graph here is showing the shear forces acting upon storeys in this model coming from load case 201, which is a pure wind load case acting through the centroid of mass. You can switch to a different load case to examine the result. Storey shear can also be displayed for the seismic load case. To access the storey drift result, first select a number of nodes, one per floor. These nodes are used by Space Gas to measure displacement, then calculate the drift. Space Gas calculates storey displacement, which is the displacement relative to the ground, storey drift, which is the difference of displacements between two consecutive storeys, and storey drift ratio, which is the difference of displacements between two consecutive storeys divided by the height of that story. The drift wind load case example, shown here, comes from the wind load alone. In a real design, you should consider the combination case which combines wind load, self-weight, and live load as appropriate because the gravity load helps reduce the drift. This is the end of the video. Hope you have enjoyed the video.